Okay, so we are going to continue from where we ended yesterday. So we are looking at how to compute entropy change. And we are saying that in order to be able to perform an entropy balance, you should be able to compute the entropy change for a system. Because we realize that everything that we try to balance, you look at some form of change as well. At a point, when we're looking at balancing mass, we looked at mass coming in, mass coming out, and then some amount of mass that will be changing within the system. We did the same thing with energy. So for us to be able to compute, or for us to be able to work with an entropy balance, we should also be able to determine the change in entropy for the system. Now, when we start with the first law of thermodynamics for a closed system, you're already familiar with this. Sorry. So we have the U tube equal to dq plus dw, right? For processes that are internally reversible, then we can have this expression we have down here. So we're looking at the small change in heat and then the small change in work, right? For internally reversible systems. So if I make dq the subject, it becomes du minus dw. Then I can do it for an internally reversible process and then have the symbols this way. Okay. Another thing is that remember we also said that dq we can represent it with TdS, and we said that dw we can represent it with minus PdV, right? So if I should put those two expressions in this expression we have here, I'll have TdS to be equal to du plus PdV. Is that okay? And this is in the extensive form because you can see the capital letters. If you want it in the intensive form, we can divide by mass. Then we'll have it in the lowercase letters now. Now remember we also said that our enthalpy H, we can represent it with U plus PV. So if I make U the subject in that case, then U is equal to H minus PV. And I can now find the differential of the expression. So if I should differentiate U, I'll get the U. If I should differentiate H, I'll get the H. If I should differentiate the minus PV term here, because it's a product of two terms, I'll use the product rule. So I'll keep the first one constant and differentiate the second one. That's what we have here. Then I'll keep the second one constant and differentiate the first one. That's what we also have here. So now this du that we found, we can put it in this expression. We can put it back into this expression. So if I should put du back in here, I'll end up with dh minus pdv minus vdp, then plus the pdv term that was left. So that's what comes here, right? So the pdv and the minus pdv can cancel out each other, and I'll be left with TdS to be equal to dh minus vdp. Is that okay? So we are building up to a certain point. So we can say that our TdS is dh minus vdp. Once again, this is in the extensive form because we are seeing the capital letters. We can divide through by the mass of the system and then get it in the intensive form. Okay. Now we are seeing here that TdS is equal to dH minus VDP. But we also earlier said that TdS can be represented with du plus PdV, right? So we have those two expressions. We have this expression and we have this expression that we can work with. Now, when we are dealing with substances that cannot be compressed or uncompressible or incompressible substances, we're saying that their volumes wouldn't change significantly, right? So it means that this dv term here can go to zero, or our PV expression, we can take it to be zero. So all that will be left with is TdS is equal to du. And we see this when we are dealing with liquids and solids. So I can say that TdS is equal to du for substances that are incompressible. Then I can make um du, in this case, du will be equal to the H. And we said that we can represent that with C dt, where C is our heat capacity. Is that okay? So we can represent it with C dt. So I can replace the du here with the C dt. And then what we can see now is that it will become TdS is equal to C dt. We can make the S the subject now, and we'll have C dt over T. So that's what we see here. Now if we integrate both sides, so I can integrate this side and I can integrate this side from S1 to S2, from T1 to T2. If I should integrate the left-hand side, I'll just end up with S2 minus S1. If I should integrate the right-hand side, right, what's going to happen is that we have 1 over T dt. So that's why we are seeing the natural log expression coming in there. And then the C, we are taking it to be constant. Is that okay? So you're assuming that the heat capacity is not temperature dependent, or it's a constant. So we are just going to bring it out and then do our integration. Okay. Now we can look at what happens when we are dealing with ideal gases. So we've looked at what we can expect for solids and liquids. Now when we're looking at ideal gases, we still have the relations we were considering. That TdS to be equal to the U plus PdV, or to be equal to the H minus VdP. But remember that we said that du can be represented with CVdT and the H can be represented with CPdT. Another thing to note is that for ideal gases, from the ideal gas equation, PV is equal to RT, we can make P the subject or we can make V the subject, and we get these two expressions we have here. The reason why we are doing this is because if we look at the first expression up here, realize that the U over here, we can replace it with the CVdT, and then the P over here, we can replace it with RT over V. So when we do that, we end up with this expression. TdS becomes du, which is CVdT, plus P, which is RT over VdV. And then we can divide through by T so that the S will stand alone and then integrate both sides. So when we do that, we end up with this expression we see here. So when we divide through by T, we end up with CV over T. Then RT over T will just leave us with R. And then we have a 1 over V. So we can integrate and then we get the expression in this form. In the same way, if we had worked with this expression instead, then the H minus VdP, and we follow the same format. So we replace the H with CPdT instead, and we replace the V with RT over P instead. We'd rather end up with this final expression down here. So if we look at it critically, realize that for the two expressions, there's one that we can work with when we are dealing with temperature and then the volumes. And there's one we can work with when we are dealing with temperature and then the pressures. Right? So it depends on the parameters you can easily get from a given question. Okay. So are we fine with this so far? Okay. So okay. So these are the two expressions that we are also going to really be making use of. S2 minus S1, we can represent it with this, or we can represent it with the one down here. Now, if we are assuming that the heat capacities are not going to be dependent on temperature, right? So we can assume that maybe they are constant and we are doing an integration. I can bring the CV out. I can bring the CP out. When I do that, what's going to happen is that I'll just be left with 1 over T dt. And you know that if you integrate 1 over um, x dx, you get natural log. So that's where the natural log expressions are coming from. The same thing happens with the volume and then the pressure terms as well. So if we should actually do the integration, we are going to end up with these two expressions now. Remember, we said that we are doing this assuming that the heat capacities are going to be independent of temperature, or they are going to be constant. So we end up with these two expressions, right? But then if we are working with a case where the heat capacities are not constant, then what happens is that we can't just bring them out of the integral and then do the integration, right? They'll have some effect. So what we do is that we have to use a different approach to get our expression. And this is what we do. So if we are working with the one that was working with temperature and pressure, for example, realize that the integral is being done from T1 to T2. So we can break. Hello. Okay. So we can break it up into two. So we are doing 90. Okay. We are doing the integration from T1 to T2. We can break it up into two. So what I can do is that I can say that that part of the expression, what I see over here, that part of the expression. Hello? Okay. Instead of me taking it from T1 to T2 directly, I can represent it with 0 to T2 minus 0. Please, can you hear me? Okay. So instead of us taking it from T1 to T2, what we can do is that we can say we are going to break the integral into two parts. So from 0 to T2, then minus from 0 to T1. So let's say I have um, a graph here, right? And I'm moving along a path to get to a final state. So this is 0. And then let's say this is going to be point 1. Then let's say this is going to be point 2, right? If I'm doing my integration from 0 to T1, and I'm doing my integration from 0 to T2, it can be this way. But then realize that we want to move from T1 to T2. So what I can do is that I can reverse this one over here. So I can take it from T1 to 0 instead, and then from 0 to T2. Right? So if I'm starting at 1 and I want to end at 2, I can move from 1 to 0 and then from 0 to 2. So that's what we are just trying to say over here. So here, the negative here. So negative here means that even though we are looking at the integral from 0 to T1, we are actually moving from T1 to 0. So that's the same as moving from point 1 to point 0. Then we can move from point 0 to point 2. So that's what we see from this part here, the integral from 0 to T2. So what we can, or what we are just trying to say is that because the heat capacity is not going to be constant, we can't bring it out of the integral and do the integration. So we have to break the integral into these two forms. Now, whenever we take something from a 0 point or from a reference point to what we are looking at, we can say that it becomes a standard property. So if I'm looking at the enthalpy at a particular condition or the enthalpy change with reference to a particular condition, right? I can say that this is going to be some form of standard um, enthalpy. So we have these entropy values over here. And we read these ones, realize that we are dealing with air. So we can read these ones from the air table, right? So the expression for Cp over T, the integral from 0 to T2, we can represent it with this. And we can read this from the air table. Then the same thing for 0 to T1. We can represent it with this. We can also read that from the table. So that part of the expression just becomes the S at T2 minus the S at T1. Then we will just do a normal integration for this part to get the minus R ln P2 over P1. So if we had a question where we were told that the heat capacities were constant, then it means the expression that we are going to be working with will be these expressions. If the heat capacities are not constant, then we'll work with these expressions. And with this expression, we'll read these two values from the ideal gas properties of air table. So do I have that one open? Okay. So that's what we have here. Okay, let me get to that page. So we have the ideal gas properties of air. So let's assume our T1 was 230 Kelvin. So we'll read the value here. Let's assume our T2 was 250 Kelvin. Would have read the value from here as well. So that's how we go about this. Okay. So we have an example here, and I would walk you through the example and then we'll come back. So I'll walk you through this example and then this one we'll leave it as an assignment for you to try. It is similar to something we did where we're looking at um, throttle valves. Right, so I'll give you a general idea of how to solve it and then I want you to try it out and then send me your solution by the close of the day. So we'll go through this example right away. I think I've already sent the solutions to you guys, but let me just share that screen. Okay, so the question says that an inventor claims to have developed a device requiring no energy transfer by work or heat transfer, yet it's able to produce hot and cold streams of air from a single stream of air at an intermediate temperature. The inventor provides steady state test data indicating that when air enters at a temperature of 39 degrees Celsius and a pressure of 5 bar, separate streams of air exit at temperatures of 18 degrees Celsius and 79 degrees Celsius respectively. Right. So we are saying that someone has said they've invented a device that can take air at 39 degrees Celsius and then it's going to split it into two streams. One is going to be cold air, one is going to be hot air, right? And then the cold air is going to come out at 18 degrees Celsius. The hot one is going to come out at 79 degrees Celsius. The one coming in is coming in at 5 bar. Then the ones coming out are coming out at 1 bar. Now, the rest of the question says that 60% of the mass entering the device exits at a lower temperature. So it means whatever is coming in, 60% of it would go out to the cold stream. It means 40% to go out to the hot stream. So we are going to evaluate the inventor's claim, employing the ideal gas model for air and ignoring changes in the kinetic and potential energies of the streams from inlet to exit. So remember when we spoke about solving thermodynamic problems, you said that um, there's a point where we need to have a schematic that would represent what we are doing so that makes it easier for us to solve the question. So let's say this is the device that the inventor claims um to work, right? We have air coming in at 39 degrees Celsius, 5 bar, and then the flow rate of the air, we're taking it to the M1. So I had to put um, a dot at the top to represent the fact that it's a flow rate. Now the inventor is saying that there's one stream that is going to come out. So that's going to be a cold stream. And that one is coming out at 18 degrees Celsius and then at 1 bar. So it also has its flow rate M2. Then there's a hot stream that will come out at 79 degrees Celsius, also at 1 bar, and it has its flow rate M3. So now we are being asked to verify the inventor's claim. For the claim to be true, the device should not violate any of the laws of thermodynamics we've looked at so far. So both first, second laws. If it violates any of the laws, then it means that it can't be something that would actually work in reality. So if we consider the first law of thermodynamics, we need to check to make sure that mass and energy are balanced. So we know that M1, what is coming in, will be equal to the sum of the outlet streams. That's M2 and M3. And M2, the question told us that 60% of the inlet um, was for the cold stream. So M2 is 0.6 M1, right? So we can put that expression 0.6 M1 back into this first expression and make M3 the subject. So when we do that, we have M3 to be 0.4 M1. Now let's check for the energy if it's balanced. So what we are saying from here is that for mass to be balanced, we already know that M2 is 0.6 M1. So it means M2 should be 0.4 M1. So now let's check the energy balance. Now the question told us to ignore kinetic and potential energy changes. They also told that there is no heat or work being transferred. So in effect, if we are taking out kinetic energy, this goes away, this goes away. Potential energy, this goes away, that goes away. Heat and work, this goes away, that goes away. So all we are left with are the enthalpy terms, right? All we are left with are the enthalpy terms. And okay, so that's what we're just talking about now. So we know the enthalpy flow for all the inlet streams should be equal to the enthalpy flow of all the outlet streams, right? So we have just one inlet, so we'll just find the enthalpy flow for the inlet, for that one inlet. It should equal to the sum of the enthalpy flows of the outlet. So that's what we have here, M1H1 being equal to M2H2 plus M3H3. Right, so this is for the inlet. These are for the outlets. Now, we already know that M1 is the same as M2 plus M3 because we said that we expect mass to be balanced. So what is coming in, the mass flow, what is coming in should be equal to the sum of the mass flow, so what is going out. So M1 is equal to M2 plus M3, right? So I can expand that further to have M2H1, M3H1, and I can now group like terms. So everything with M2 goes to one side, everything with M3 goes to one side. I can factorize M2 and M3 out. Now we are assuming that the heat capacity is constant. So for air, the Cp of air is 1.005 kilojoule per kilogram Kelvin. When we're looking at a change in enthalpy, remember we also said this when we're looking at the first law, H1 minus H2, right? Or the change in enthalpy. If we are dealing with constant heat capacity, we can represent it with Cp times the change in T, right? So in effect, this part here becomes M2 times Cp, T1 minus T2, because we're moving from H1, we are looking at H1 minus H2. And this part also becomes M3 Cp, T3 minus T1. But then we have the same Cp value, so they can cancel out, right? And we also said that, hello. Okay, so we said M2 was 0.6 M1, and then M3 was 0.4 M1. So I can put them into the expression, and then the M1 terms can cancel out. So I'll be left with this stream, T3, which is the temperature of the hot stream, and then T1, which is once again the inlet temperature. And if I should compute this, I'm going to have 12.6 to be equal to 16, which is impossible. So we need additions. right? So if we should compute it, realize that they are not equal to each other. So the energy is in balance and the device can't operate at the hello. Okay. But now if we had solved the question and the energy and mass were balanced, right? It means that the first law um, would hold, and we can now go further to see if entropy would be generated, or we can check the second law. Remember, for the second law, we said that SGen has to be greater than or equal to zero. So that's what we're just going to check now. So if we had done it and then mass and energy were both balanced, then we would have just checked with the entropy expressions as well to see if our SGen is greater than or equal to zero. If it is not, then the inventor's claim is false, right? So we are told that there is no heat transfer, so we can cancel out the term involving the heat. And we are just left with our change in S to be equal to our SGen, right? So our change in S, let's consider the entropy coming in from all the inlets and the entropy leaving from all the outlets as well. Just the same way we did for our change in enthalpy. We can do the same thing for our change in entropy. So it's going to be M1S1, right? Minus, so this is the inlet M1S1 minus the outlet M2S2 minus M3S3. Now, we are saying that all of that should be equal to our entropy generated. So M1S1 minus M2S2 minus M3S3 should be equal to our entropy generated. And just like what we did when we we're looking at the enthalpy, M1 is M2 plus M3. So I can expand and then I can group the terms. So everything with um, M2 can go to one side, everything with M3 can come to this side. And I can factorize M2 and M3 out. So if all of them should be equal to my S generated. But you remember that we had these expressions. So if I have S2 minus S1, this would be the expression we can use if you are dealing with temperature and volume, or the one down here if you are dealing with temperature and pressure. So we looked at that just when we started this particular lesson. So we're going to work with the one involving temperature and pressure because we have those parameters already. They are easily accessible from the question. So this is the expression that we are working with right now. And we are saying that if I have SA minus SB, I can represent it with CP link TA over TB minus R link PA over PB. So I know S1 minus S2. I'll just replace T and TB with T1 and T2, and then PA and PB with P1 and P2. And I already know my CP value, so I can put that in there and then get this value. So when you're trying it out, confirm the answers, right? You can do the same thing for S1 minus S3, and then we get that value. So we can put them into the original expression, what we had here, the original expression here. We can put these values in there. So I'll have M2 times that plus M3 times that to be equal to our S generated. But once again, we said M2 was 0.6 M1, M3 was 0.4 M1. So we can factorize M1 out, and then we can simplify what is inside. We're going to get a negative answer. So if I divide our S generated by the mass of what is coming in, I'll get it in an intensive form. But then the answer is negative, which is impossible. So you remember that we said if our edge generated is greater than or equal to zero, it's irreversible. If it's equal to zero, it's reversible. But if it's less than zero, it's impossible. And since we are seeing a negative value here, it means that it's impossible. The inventor's device will not work. But the inventor's claim is false. So that's it for this question. For the next example, we are told that steam at 7 megapascal and 450 degrees Celsius is throttled in a valve to a pressure of 3 megapascal during a steady flow process. So when we're looking at throttling valves, we looked at something very similar. And we said that when we are dealing with a throttling valve, the enthalpy wouldn't change, but then the temperature can change with pressure as well. So if I'm having 7 megapascal and 450 degrees Celsius, I'll find the enthalpy there. Then with that same enthalpy and with the pressure I have at the exit, I'll find the temperature there. So I'll look at the enthalpy I have. I'll look at the pressure I have. Use that to now find the temperature of the outlet. Now we have temperature and we have pressure for both the inlet and then the outlet. So for us to determine the entropy generated, right, we can come back to work with this expression here. So I want you guys to try that out, and then you can send the solution by the close of the day. Okay. Now we are looking at isentropic processes. When we say something is isentropic, it means that its entropy is constant. And there are certain relations that we need when we are dealing with isentropic processes. So we are going to first consider a situation where we have constant heat capacities. And we realize that we said when we have constant heat capacities, we're working with these expressions. So the expressions we had over here for constant heat capacities. Now, if we are saying they are isentropic and there's no change in entropy, then it means that this goes to zero because there's no change in entropy. And then this also goes to zero because there's no change in entropy, right? So the rest of it is just change of subject and mass. So all we are doing is that for the first expression here, when this goes to zero, you can make T2 over T1 the subject. The second one, when this goes to zero, you can make T2 over T1 the subject. But one thing that would help you as you continue solving is the fact that you get to a point where you have R over CV or R over CP, depending on which one you are solving. And we remember that we said R is equal to CP minus CV. Sorry, someone tried calling me. So we bring okay. So the R value we have here, we can replace it with CP minus CV, right? And if we simplify even further, we'll get to a point where we'll have CV over CP or the other way around. And remember that we said that um if we have CP over CV rather, right, we'll be getting K. So we have, I think I have it here. Okay, it's here. So we have, if you want to go through the algebra in the math, you can go through, I think I've sent this to you as well. So I did everything step by step. So S2 minus S1 is 0. We'll have CV ln T2 over T1 plus R ln V2 over V1. Then we can send the R ln V2 over V1 over the equal to sign. And then we'll just end up with this expression here. Then I can divide through by CV to get this. But we said that, okay, even before that, I have this as a coefficient of a natural log. So it can become a power, right? Then they both have natural log on both sides. So we can take the natural log out. And then we said R is equal to CP over CV, CP minus CV, right? So I can replace the R here with CP minus CV. Then I'll end up with minus CP over CV minus CV. But then we said CP over CV is equal to K. So I can replace the minus CP over CV with the K. And I'll end up with minus K plus 1. So that's the expression that we are looking at, right? So we can do the same thing with pressure. So we can use this expression instead. Make S2 minus S1 0 because it's isentropic. Send this part over the equal to sign. And we get this expression here, right? Divide the R with the CP so that we get this one here. We can now make it an exponent. So we can send all of this over to become an exponent here. So that's what we see over here. They both have natural log, so we can just equate what is inside to each other. Once again, R is CP minus CV. So we can simplify when we end with this. But we said CP over CV is K. So CV over CP will be 1 over K. So I can put that in there, simplify the exponent again, and I end up with this expression, right? Then we can also relate pressure and volume. So the two expressions we just found are these. If they are both equal to T2 over T1, then they are equal to each other. So I can equate them to each other, and I can just make P2 over P1 the subject. So I can take my time, go to the simplification. And when I do that, I'll end with this. So I've sent this to you. You can go through step by step later on. It's just math, change of subjects, algebra, those things. So we'll spend too much time there. But at the end of the day, we are expecting certain expressions that we can work with. And those are the expressions we see here. So a relation between temperature and volume, temperature and pressure, then pressure and volume. When we are dealing with isentropic processes with constant heat capacities. Right. Okay. So all that we are saying is that we can take the expressions we use for the change in entropy at constant heat capacity. If it's isentropic, S2 minus S1 is 0. We can make T2 over T1 the subject. When we do that, we'll end up with an expression. Wherever we see R, remember we can replace it with Cp minus Cv. And wherever we see Cp over Cv, realize that we can replace it with K, right? So we just do those substitutions, those change of subjects, and we end up with a final formula. Now, one other thing to also take note of is the fact that PV to the power K is equal to C. Hello. Okay. We saw this when we're dealing with polytropic processes where PV to the power N is equal to C. Hello. What we are saying is that from this relation, right, we can derive this. So if I make P2 V2 equal to, or P2 V2K, right, you realize that it means that they are always going to be equal to a constant. So what I'm saying is that if I should express this further, then I can say that the power K should be equal to P1 V1 to the power K. So it means for every pressure, hello, okay. So for every pressure and volume at a given state, it's always going to give me a constant. So P2 V2 to the power K at every point is going to give me a constant. And this works when we are dealing with adiabatic processes as well, right? So if something is, okay, well, I think we would get there. So we can also look at variable heat capacities. And remember we said when we are dealing with variable heat capacity, this is the formula we are going to use. So if I want to make, or once again, we are dealing with an isentropic process. So the change in S goes to 0, right? So it means everything on the right-hand side is equal to 0. So I can make P2 over P1 the subject. And then if I do that, I end with this, right? So once again, try it out. If you get stuck, you can reach out to us. But we'll make P2 over P1 the subject. When we do that, we can simplify it even further to get the next expression. So here we just have exponential of two things being subtracted. I know if I have exponential a minus b, the same as exponential a over exponential b. So that's what we see here, right? Now this term up here gives us what we call the relative pressure. at that condition. Is that okay? So what we are saying in effect is that when we are dealing with variable heat capacity, the ratio of P2 to P1 is the same as the ratio of the relative pressure at T2 and the relative pressure at T1. So this, we read it from, remember when we're doing, when we're expressing this, we read these ones from the ideal properties of air table. We'll read these ones as well from that same table. So we have them over here, right? These values, the PR values, the relative pressure values. So we can read those values as well. So at a given temperature, we can read their value, right? Okay. So that's what we are just trying to say. The ratio of the pressures will be equal to the ratio of the relative pressures at that temperature or at those temperatures. In the same way, if we had used the expression that was working with volume instead, right, and not pressure, would have ended with this expression. This is also the relative volumes at the given temperatures. So once again, we can read those ones from this table, right? So that's something to take note of. Okay. Now let's consider isentropic work that is being done for a turbine or for incompressible fluids, for a turbine and then with incompressible fluids. So remember we said that CDS, we can represent it with BH minus VDP. That's when we started today's discussion. We made mention of this. And we're saying that if it's isentropic, that means S is constant. So this DS term here can go to zero. So all that we are going to be left with is DH is equal to VDP. That's one thing to keep note of. Then we also said that if you're looking at the first law, the change in the work plus the change in the heat will be equal to the change in the enthalpy. So this is a change in the shaft work, change in the heat. This is a change in the enthalpy. So this is the energy balance for open systems, right? When we neglected kinetic and then potential energy. So we have here our DQ. Remember we said DQ, we can represent it with TDS. So I can replace DQ here with TDS to get this expression. And once again, we are dealing with constant entropy. It's isentropic, so the ds can go to zero. So all that I'll be left with is dws is equal to dh. That's what we have here. But remember we said dh is equal to vdp. And here we are saying dh is equal to dws. So that means that dws is also in effect equal to vdp, right? Now, if I want to find the work that is being done by the turbine, right? So that's the WS, the shaft work there. I can integrate the whole expression. So if I should integrate the WS, I'll just get the total work that is done. If I should integrate the DH from H1 to H2, I'll get this. And if I should integrate the VDP, right, from P1 to P2, I'll get this expression. So from P1 to P2. Now, if it is incompressible, it means the volume is not going to change significantly. So the volume is almost constant, right? So if the volume is constant, I can do my integration easily, and I'll end up with my W to be equal to this. That's after I do my integration. Because the volume is a constant, I can bring it out. And if I'm integrating 1, it just becomes P from P1 to P2. I put those values in, I get my value for W, or my expression for W, right? In the case where the fluid is compressible, so the volume is not constant, we would need a relation to work with. So we go back to our polytropic relation. Remember we said PV to the power n is equal to C, right? And we're saying n can have different values. N can be 0, 1.4, 1. Depends on the kind of system that you are working with. Is that okay? So if n is equal to 1, we are dealing with an isothermal process. So PV is equal to C is equal to RT. So all that we're about to do here again is also algebra and math, right? So I've also sent the step-by-step solution for those who want to go through the math or who might be going through and might get stuck. So I'll take you through it generally, but then I actually advise that try it out, right? If you get stuck, try again, try again, try again. And then if you are not getting it, you can now refer to what I've sent you, or you can reach out to me, and then I'll help you out with that. So let me project that slide. Which one was it? Okay, I think it's this one. So so we are saying that we have our WS to be equal to our VDP, and then we know that PV to the power n is equal to C. So when n is equal to 1, PV is equal to C, which is equal to RT. So if RT is going to be a constant, R is already a constant, it means T is a constant as well. That's why it's isothermal, right? If T wasn't a constant, we can say that the product is equal to a constant. So I have PV is equal to C. Now I can make P the subject and get C over V. Then if I should differentiate with respect to V, if I find dP dV, I'll have this expression. So I know we are all familiar with differentiation. We don't have to teach differentiation here, right? But then I can make this V to the power minus 1. Then I'll differentiate and have minus 1 times C V to the power minus 2. Then I can simplify it further to this. Then I can make dP the subject. So I'll have minus C over V squared dV. And I can now put that expression into the first equation. So I can put that expression here. So I'll replace dP here with this. So when I do that, I'll end up with this. Now the V here can cancel out one of the V here. So that I end with this expression over here, right? And we are dealing with the fact that, or we are dealing with the assumption that our heat capacity is constant. So I can bring it out. So I'll just have to integrate 1 over V. And if I integrate 1 over anything, 1 over V, I'll get the natural log of V from V1 to V2. So I can put V2 in minus, I'll put V1 in. Then remember we are dealing with log or natural logs. Ln something minus ln another thing. It's just going to be ln of the ratio of the two things. So if I have ln A minus ln B, the same as ln A over B. And we said our C is equal to our RT. We also know that from PV is equal to RT, right? We can say that V is equal to RT over P. So if I'm looking at V2, it's going to be RT over P2. Remember, temperature is constant, so it's RT over P2. If temperature wasn't constant, would have made it T2, right? But temperature is constant, so it's RT over P2. Then for V1, it will be RT over P1. So since they are divided, we can divide their expressions in here. Then we can reciprocate this one here so that we have this expression down here. Right. Then RT can cancel out and we end with minus RT ln P1 over P2. So if we check the slide, realize that that's the expression we ended with for work done in an isothermal process. We ended with RT ln P2 over P1. Is that okay? What is the wrong one? Okay, so that's it. Right. So we ended with RT ln P2 over P1. So you see we are having P1 on P2. It's because of the negative here. If I send a negative over to become an exponent, the P2 and the P1 will now reciprocate. So from the rules of dealing with logarithms, right? If I have minus ln A over B, it's the same as ln B over A, right? So if I get rid of the negative, it becomes the P2 over the P1. Now, if you're dealing with an adiabatic case, then we are saying that our N is equal to K. So PV to the power K is equal to C, right? So now once again, the same procedure. I'll make P the subject and I'll have V over K, or C times V to the power minus K. And I can put that into equation 1. So if I put it into, oh sorry, I have to differentiate first. So I'll find the PdV, right? And if I'm finding the PdV, the V to the power minus K here, I can bring minus K down, then I subtract 1 from the power. the normal rules of differentiation. So that's going to give me this part here, right? Then I can factorize negative out in the exponent to have minus k plus 1. Is that okay? And I can decide to simplify it further to have minus kc over v to the power k plus 1. So I can make dp the subject by sending dv over to multiply the expression. And I can put that into equation 1, right? What's happening over here is that if I have if we have v to the power minus something, let's say minus v is equal to 1 over, hello, yes, it's equal to 1 over v to the power a. So if I'm having v to the power minus k plus 1, that's why I thought negative out, so that I can easily do this. Hello, okay. So that's why I factorize the negative out, so that I can easily do that. So I can make it kc over, hello, okay. So I can make it kc over v to the power k plus 1. And I can put that expression. Hello, 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 okay. So if I put that into equation 1, right, I'm going to replace the dp here with this whole expression here. So if I should put that in, this is what I'm going to get. Now, if you look at the denominator, it is v to the power k plus 1. Know that if I have anything to the power something plus something, right? Let's say I have v to the power k plus 1 in this case. It becomes v to the power k times v to the power 1. So remember that if they have the same base and they're multiplying, we add their exponents. So v to the power k plus 1 can be written as this. So that's what we've done down here. Then this v here can cancel this v over there, right? Okay. So the v's can cancel out, and then we'll end up with this expression we see at the bottom here. So we end up with this expression here, and we can decide to make it minus kc v to the power minus k. Now, if we should do our integration, the minus k here, remember minus kc is a constant, so we can bring it out. So I'm just going to integrate v to the power minus k. So if I'm integrated, I'll add 1 to the power. That's minus k plus 1, and I'll divide by that power minus k plus 1 from v1 to v2, right? Then we can factorize the negative out. So if I factorize the negative out, the denominator will become k minus 1. Then the negatives can cancel out. So when the negatives cancel out, I can now put in my v2 and my v1. Oh, yes, and we can also factorize k over k minus 1 out. So you can factorize that out. Because k is a constant, that whole expression is going to be a constant, so we can factorize it out. And then we can end up with the expression in this form. So I can now put in my v2 and my v1, and then find the difference between them. And then once again, I have v2 to the power minus k plus 1. So just like what we did over here, we can make it v2 to the power minus k times v2 to the power 1. We can make this v1 to the power minus k times v1 to the power 1. So that's what we've done over here. Then we also know that from what we said that p was equal to c over v to the power k. That's what we said at the start, right? So everywhere I see cv minus k, I can replace it with p. So if it is v2, or if it is cv2 to the power minus k, I can replace it with p2. And then cv1 to the power minus k, I can replace it with p1. So that's what we've just done here. Then we also know that pv is equal to rt. So p2v2 will be equal to r times t2. Then p1v1 will be equal to r times t1. So realize that this is for adiabatic, not isothermal. So we are not using the same temperature for both of them. So if I replace P2V2 with RT2 and P1V1 with RT1, I'll get this expression now. So I can factorize um, R out, right? But even before we do that, from what we saw when we're looking at the isentropic relationships, we had a relation for T2 and P2. Is that okay? So the reason why we're doing this is because we are dealing with the work. We want to see what happens as we are changing the pressure because we are dealing with a turbine. So we know that there's going to be some kind of pressure difference, which we can easily measure. So we want to work with pressure as well. So I can replace T2. I can make T2 the subject, and I can replace T2 in this expression with this new expression, right? So if I do that, I get this, and I can now factorize RT1 out. So if I should factorize RT1 out, I'll now have this expression, and that's the final form. So that's what we also see when we come back to the slides. I think it's this expression here, right? So that's the expression that we see. Now, if we are looking at a polytropic process, it means that now PV to the power n is equal to C. It's the same procedure we are going to use for PV to the power k to be equal to C. So this time the k just becomes n, and we'll end up with the same expression, right? So that's it for the proofs of those relationships, right? So these are things that we need to know. So if you have a question where you're supposed to find the work being done by um a work being done when there's some compression being done, you have the pressures at the 2 points, so at your inlet and your outlet. So usually they call it the compression ratio, right? The ratio of P2 and P1. So you have your pressures, you can put them into your expression and you can use it to find your work. So if it's isothermal, you are working with this expression. If it's adiabatic, you're working with this expression. If it is any other process and you have a value for n or you've been given a value for n, you work with this expression and put that n value in there. Okay. So now let's look at compressing gases a bit further. So we are saying that what's the best way we can compress a graph? If we check the best way we can compress a gas, if we check the graph on the right, you realize that when we look at an isothermal process, the amount of work we have to do is smaller to get our system from point one to point two. And how do we say we find the work of a process like this? We have a PV curve. You can just look at the area under the curve. So the area under the isothermal curve is way smaller than the area under the um polytropic curve, right? So we are saying that if you're compressing um a gas reversibly and adiabatically, it's the least energy efficient way of doing it. The one that is going to be very energy efficient is to do it reversibly and isothermally. So the most compression techniques are designed to approach isothermal compression. Is that okay? Okay. So we can look at multi-stage compression with interstage cooling. So instead of, well, let's look at the graph we have over here. We want to move from point one to point two. Instead of moving directly from point one all the way to point two, right? We can employ multi-stage compression with interstage cooling. It means that we compress to a certain pressure in between the pressure we are at and the pressure we are looking for. We cool it a bit because when you compress a gas, it will heat up. You cool it a bit, then you can compress it further, right? So if it was an isothermal process, it should have just been this black line over here. But we can make our system more efficient. If it was polytropic, it should have gone this way. So to make it efficient, we can compress it to px. We can cool it, right, to the temperature where maybe it would have been isothermal. And we can compress it further to point two. So we can do we can do things this way. So now instead of us taking it from P2 to P1, we're going to take it from PX to P1 first, and then from P2 to PX. So we are moving from P1 to PX, and then we'll use the same relation, move from PX to P2, right? And the expression for PX is just P2 times P1 to the power 0.5. Okay, so it's P2 times P1 to the power 0.5. Or we can use the expression Px over P1 should be equal to P2 over Px. Is that okay? So if they are going to be equal, then it means that what is in here, Px over P1, is equal to P2 over Px. So in effect, they are the same expression at the end of the day. And if I'm adding two of the same expression, if I have A plus A, my final expression is 2A. So realize that the work that I'm going to get is twice the work um, of compressing it from maybe just P1 to Px, right? So it's just going to be two times the work I would get from compressing from P1 to Px. Okay. Now we can also consider how efficient our systems are, or how efficient our systems can be. We know that if there are irreversibility in a system, right, it's going to degrade or downgrade the performance of the devices that we are working with. So when we are doing analysis in engineering, we want to be able to determine some parameters that would help us be able to determine the extent to which this degradation is going to happen. So what I mean by that is I can have a system. I want to be able to analyze my system in a way that I'll know that okay, this is how um much energy I can get out for what I'm putting in. And that's where efficiency comes in. So what we do is that we compare the ideal process, right, in which the actual process is happening to an isentropic process. Is that okay? So we are looking at isentropic efficiency. Efficiency when we are considering that the system could have been running at a constant entropy. So our entropy change is zero, usually representing the fact that it can be reversible, or a point where we can have a maximum um, work output for a smaller work input. I think we spoke about all of that yesterday, right? Then we are dealing with isentropic efficiency. So when we are dealing with a turbine, the formula for isentropic efficiency is what we see here. Is the actual work divided by the isentropic work. We'll talk about that very soon. We are dealing with a compressor. It's rather the other way around, right? So the reason is that if we are dealing with a compressor, normally we are putting in the work, right? And you know that if you are looking at efficiency, we can consider um input, we can consider sorry output over input. So the thing that we are actually putting in, we are going to consider that to be our actual work, right? So if you're looking at a compressor, we are taking it that we are putting in some form of work. So since that's going to be our input, that would be a denominator term here. The isentropic work is what to come at the top. When we are doing dealing with a turbine, okay. When we are dealing with a turbine, right? We are assuming that it is the one that is doing work, so we can consider that actual work more of more of, hello. Okay. We can consider that work more of an output. So that one will rather come at the we have an isentropic work at the base here. Now, if you're looking at the actual work that is being done, realize that we are doing a compression or a expansion from H1. H1 is okay. So H1 is the point we are um Hello, hello, hello. Okay. H1 is the point that we are um starting from, right? The path that we actually take, we end at H2. That's the actual enthalpy we end at. So that's why it's the actual work. If you find a difference between them, is the actual work, right? And in this case, you are considering that H1 is higher than H2 because we are dealing with a turbine. So the enthalpy of what is coming in will be higher than what is coming out because you're going to cause it to expand. So the enthalpy of what is coming out will be lower than what is coming in. And then when we consider H2S, that is the enthalpy it would have ended at if we assume we're dealing with a... Hello? Okay, sorry, few network issues. So what I was saying was that if we are looking at um an isentropic process, right? So we are starting at H1 and we are ending at H2A. That's the path we actually follow. And if you check it, realize that the entropy is going to increase. So this is an enthalpy entropy diagram. So at H1, the entropy was S1. But then when we perform the actual process, the entropy is somewhere here. So we can see a change. If it is isentropic, then we are assuming that the process is going to occur while the entropy stays the same. So you're moving from H1 down to the exit pressure, right? But then we are not going to ensure that entropy changes on the x-axis. So it's a straight line down. The same thing happens when we are dealing with a compressor. So for a compressor, we are rather taking a gas and then pushing it together, compressing it. So the enthalpy of what is coming out will be higher than what is coming in. So we have our exit pressure here and we have our inlet pressure here. What we are saying is that for the actual process, if I'm going from H1 to H2, once again, we can see that there's a change in the entropy, right? But the moment I keep the entropy constant and I move to the exit pressure, that's the isentropic process. Okay. So just take note of these formulas that for a turbine, isentropic work is the actual work over the, sorry, isentropic efficiency is the actual work over the isentropic work. And then for a compressor, the isentropic efficiency is the isentropic work over the actual work. So we have an example here. Steam enters an adiabatic turbine steadily at 3 megapascal and 400 degrees Celsius. And then it leaves at 500 kilopascal and 100 degrees Celsius. If the power output of the turbine is 2 megawatts, determine the isentropic efficiency of the turbine. So let's look at it bit by bit and let's use this graph. Right, so you're dealing with a turbine. So what we are saying is that for us to be able to find the isentropic efficiency, we need the actual work and then the isentropic work. And we said the actual work is going to be H1 minus H2A. So as we move from H1 to H2A, so I can read at the temperature and pressure that was given to us, the H1 for the inlet. And at the temperature and pressure given to us for the outlet, I can read H2A. But when I want to read H2S, that's the one for the isentropic process, right? I can't just work with the same temperature and pressure. So what I would rather do is that when I find my parameters at point one, I know that the entropy is supposed to be constant. So what I know for the exit for the isentropic process is the entropy and the pressure. I can use that rather to find a new enthalpy there. So this is what we are just trying to say. For H1, I can read it from my table. If it is air, I can read it from my air table. If it is steam, from my steam table. So I have the temperature and pressure. I can read H1. For H2A, I can also read it from the table because I know my temperature and pressure. So I can read H2A. When it comes to H2S, what we are saying is that we can't just use temperature and pressure, right? Because if we use the temperature and pressure, we are doing that for the exit, and that will give us the actual process. That's H2A. We want the isentropic process. So what we are going to do instead is that for the isentropic process, the parameters we know, we said it's isentropic. So it's going to have the same entropy as point one. So we know the entropy for H2S, and then we know the exit pressure as well. So I'll rather use these parameters to find my enthalpy. So let's look at the question again. So we're told that we have a formula for the isentropic process. That's the actual work over the isentropic work. And we are working with steam. So let me put the screens together. Let me share that instead. Okay. So we are looking at steam. So let's look at steam at a different condition. We have first the inlet at 3 megapascal and then at 400 degrees Celsius. So let's check for 3 megapascal. If I come to the superheated steam table, right? 3 megapascal, 400 degrees Celsius. So this is for 400 degrees Celsius. And then the enthalpy is the third column. So the value I'm going to read is 3231.7, right? It's going to be this value over here. So that's what we see being done at this point. Oh, let me plug in that. Okay, that's what we see being done at that point. Now, I'm coming. We can also find the H2 actual, so the exit enthalpy, right? So for that one, the question told us that we are coming out at 50 kilopascal and 100 degrees Celsius. So if we go and check for 50 kilopascal over here, right, 100 degrees Celsius is higher than the saturation temperature that they have. So it means it's superheated. So we'll go back to the superheated table. So 50 kilopascal, if I move back to it, is the same as 0.05 megapascal. 50 kilopascal is the same as 0.05 megapascal. So I'm going to read at 100 degrees Celsius. And the value I'm going to get for enthalpy is a 2682.4. So if we continue with the question, you realize that that's what they've put down here, 2682.4 for their H2A, right? And we've already found H1 as 3231.7. So now let's continue. So that's for the inlet and then the outlet at the temperature and pressure that we're given to us for the actual process. Now let's look at for the isentropic process, the outlet, if we consider it to be isentropic. So we said if it's going to be isentropic, it should have the same entropy as the inlet. So let's go back to the inlet condition. That was 3 megapascal and 400 degrees Celsius. The entropy there was 6.9235, right? So that's what we see here, 6.9235. We are saying that the entropy is going to be the same. So at that same entropy and at the pressure we're having at the outlet, we are going to read so that we can get our enthalpy, right? So that's the exact same thing I was saying about the graph here. We are going to work with the entropy and then the exit pressure. So we have an entropy of 6.9235 and the exit pressure is 50 kilopascal. So let's go back to the part where we had 50 kilopascal. If I come to the 50 kilopascal point, right, realize that the entropy there, so that's here, these values here. If I should check, the 6.9235 is in between the entropy of the saturated liquid and the entropy of the saturated vapor. That means it's a liquid vapor mixture. So we'll find our quality. And we already know how to do that, right? So we'll find our quality. We have the entropy, we have the entropy of the liquid, saturated liquid, the entropy of the saturated vapor. We can put it into our expression and then find our quality, which is going to be 0.897 if we should do it well. Then we want to find the enthalpy for that same system. So we are going to use the quality we found, right? And then this time we are going to pick the Hg and then the Hf value and use that to find the H2S.
Is that okay? Still using the same formula. So H2S is going to be HF plus X Hg minus HF. We use the entropy with a similar formula to find the quality. And the quality of the material is not going to change. It's going to be the same material you're working with. So I'm going to put that value in here, read my HF and my Hg from the same table at that same pressure, and use it to find my H2S. So once I find my H2S, I can put all of them into this expression here, and then get my isentropic efficiency for the turbine, right? And next part of the question said the mass flow rate of the steam flowing through the turbine. So we are looking at the mass flow rate, and we know that the mass flow times the change in enthalpy will give us the work that is done, right? Sorry. And we know that they said that the power output was 2 megawatts. So that's the actual work that was done. So 2 megawatts, we can express it in kilowatts. So we have 2000 kilowatts. That's going to be the work that was done, right? So we are saying that the work that is done is just the mass flow times the change in enthalpy. Because of the actual work, we are using the actual um, enthalpy change. So it's going to be 2000 kilowatts divided by H1 minus H2A. That will give us the mass flow of what we are working with. Hello? Okay, so the last thing we will do is I'll leave this for you to also try out, right? We have here air being compressed. So air is being compressed by an adiabatic compressor from 100 kilopascal and 12 degrees Celsius to 8, if the isotropic efficiency of the compressor is 80%, we are being told to determine, right? And then you can send me your solution. If you get stuck, I would guide you through, and that will be it. So at this stage, we understand entropy and its effect, and this knowledge to power and the work producing cycle. So for thermodynamics, next segment, really. So we are done with thermodynamics for this vacation. We are done with entropy. We finished everything we set out to do. So I've sent you all the materials. Please try out the questions. They are very necessary, right? And then if you get stuck anywhere, reach out to us. We'll help you out. Okay. So are there any questions? So I'll send the attendance link right away, and we can take it from there. So that's the attendance link. So let's do also fill it within the next 5 minutes, and then we'll be done.